It's time. We're live. We're here. It's Planetarium Live, Episode 2, with yours truly. It's Ryan. This is Astronomy in Action. We're back for the second episode. I can't believe the first one was Friday. It feels like forever ago. It wasn't really that long. So I've been scrambling to prepare some really cool stuff for all of you lovely people out there. Thank you for joining in. Feel free to ask questions in the chat. That's the idea of this whole thing, is that I'm a planetarium guy without a planetarium, and I just love answering questions about space. So we've got the chat window on the YouTube Live. We tried Facebook last week. It was okay. Lovely people tuned in. We got lots of great questions. I got to ask you some questions, so it was good times. This time we're on the YouTube, so you can do your questions in the chat there. We're going to see how it works. We're going to see which one we like best, and then when we do the next stream, we'll decide which one was the better one. So we've got some fun stuff planned for tonight. We're going to revisit a couple of questions that we talked about last week, and we've got a special guest, and we've got some really cool software to show. I'm pretty excited. Because we have a special guest, I have these giant, lovely headphones on so that I can hear all the fun stuff going on without doubling and duplicating the audio. But it's okay. They're sort of stylish. I am rocking my Astro in Action t-shirt as well tonight, so I feel like I'm actually doing some legit work instead of just this fun stuff, right? But I want to introduce our guest for the evening on what I lovingly call the Jesse and Ryan cam. This is Jesse Rogerson. Say hi, Jesse.
Hi, everybody. I'm Jesse Rogerson. Ryan, thanks for having me on. I always love talking about space, and I think that you and I have talked about space together more than any other person I've talked about space with.
I think that goes for me, too.
I think that's true, because we did our undergraduate together, so I've known you since first year, and we did astrophysics together, and then we've been talking about space for 15 years or however long it's been.
And counting.
So I'm really glad to join this show.
Cool. It's going to be a lot of fun, and we've got a couple of things that I have to ask you personally as we go through the program. Not deep personal questions, but personal science, astronomy related questions.
I thought it was going to get deep, Ryan, but that's okay, fine. We'll just talk about space.
I know, I was too. The first thing I wanted to talk about, though, was something that we had a question last week that was that actually I asked. It was a poll question. It was, which month is the Earth closest to the Sun? And so it was a poll question. We had a few options. We had, I think the options were March, August, January, and November or something like that. Of course, I know that you know the answer, so I'm going to give you a chance to look extra smart in front of everybody. In what month is the Earth closest to the Sun?
That would be, what is January?
This is Jeopardy. Yes, January is correct, and that's really a little counterintuitive, right? If you have an idea that you would think more sunlight means summertime and less sunlight means wintertime, right? And so naturally, if we're closer to the sun, we should get more sunlight, and if we're farther from the sun, we should get less sunlight. And so, very counterintuitive thing, especially because it's kind of backwards, right? The middle of winter for us is January. It's cold, it's dark, it's depressing, and yet the Earth is closest to the sun, where it should be getting the maximum amount of sunlight. But there is a reason behind all this, so we're gonna bring this up here. I want to talk a little bit about the seasons. I'm just going to apologize in case there are any video issues. We are having a little bit of buffering thing. I think, with everybody doing internet stuff these days, things are coming out kind of slow, so the stream, I'm just going to say, maybe buffering. It's still up.
I think
on our end.
That's a really good question. I love talking about this question about what month are we closest to the sun, because even just asking the question is funny, because we tend to not think about that. We tend to think the Earth goes around the sun and it's in a circle around the sun, and it's sort of outside your normal way of thinking that we would even be, there is even a point where we are closer to the sun or further from the sun, because there's a point that Earth gets closest to the sun that we're talking about right now in January, and then there's a point where it's furthest from the sun. And that whole idea, the fact that we're not in a perfect circle around the sun as we go in our orbit is kind of like it's a really fun way to blow people's minds. It kind of takes you out of your everyday reality. So I like the question. Just the question in general points at gives you something to learn on right away. That, oh, wait a minute, we're not always the same distance from the sun. It's cool.
Yeah, it is. It is a fun one to think about. And I mean, I'm trying to trick people too a little bit when we're doing that. Okay. So
how far are we from the sun? The average distance. Oh, if you're going to give me a softball, I'll give you a softball. What's the average distance from the Earth to the sun?
The average distance from the Earth to the sun, 1 astronomical unit. I know, right? No, it's 150 million kilometers. 150 million kilometers. So yeah, 150 million. That's a long way, really long way. But
I can't even picture it.
Yeah, totally. I know. It's really hard to imagine, right? It's one thing to say, oh, it's the moon is 400,000 kilometers away. The sun's 150 million. Oh, those are numbers, but it doesn't really make sense. By the way, please, anybody who is listening and able to hear all this stuff okay, if you just let us know when the stream's dropping in the comments. We're doing our best. I think there are internet troubles for everybody these days, so we're just going to power through. And at the very least, if you do miss the live stream, we're going to have a recording of the whole thing on YouTube as soon as we're done. So that'll make things a little bit easier. So anyway, let's get back to the task at hand. We are here to answer, why do we have seasons though? And one of the things I want to show is this little graph here that's going to help us out a lot. The idea is not that the Earth is closer to the sun or further away. It's more about the tilt of the Earth's axis. The Earth is tilted 23.5 degrees, and this is why we have seasons. It's this tilt. And so what you can see in the image here is that tilt is always the same. No matter where the Earth is in its orbit around the sun, that tilt still points to the same direction. It's always pointing the same direction. And if you look toward the summer solstice, June 22nd, you can see that tilt sends North America pointed a little bit more at the sun. What that means for us is that the sun is a bit higher up in the sky. It means that we get a lot more direct sunlight, and it means the days are longer. 3 months later, that tilt is still the exact same, and we come over to September, and now the tilt doesn't really matter. The sun is shining kind of perpendicular to it, and so the whole Earth gets the same amount of sunlight. The equator actually gets the most amount of sunlight during the equinoxes. And then, of course, 3 months later, again, we get to our winter in the northern hemisphere, summer in the southern hemisphere, summer in Australia, and that same tilt is now pointing away from the sun in the north, and so we in the northern hemisphere get less direct sunlight. It gets colder, it's winter. The Earth is actually closer to the sun, but we're getting less of that direct sunlight. And now I'm going to actually show a couple different images of this kind of same concept. So we come over to this is a kind of a point of view of the southern hemisphere, because in Australia their winter is in June. Their winter solstice is June 21st, and their summer is in December. So it's a little bit backwards, but backwards to us, but
it's completely backwards.
But normal to everybody in Australia. I know we had I've had some Aussie friends.
We're the backward one. I mean,
yeah, right.
Paul Delaney would say that we're the backward one.
Yeah, they can tell us that. So they can tell us that that we're the backwards ones whenever they want. But there you go. And one other way that kind of helps me visualize this, Jesse, I'm going to show you this one, is that if we kind of view it from above, you can see the red circle that represents the North Pole. And so when we're at the December solstice, the winter solstice or the summer solstice, you can see that North Pole is either pointing toward or away from the sun. More sunlight gets the northern hemisphere or the southern hemisphere. It's all about the tilt. That's what it's all about.
You know what? I've never been to the southern hemisphere, and what I think would be really jarring would be the idea. So when you go out, since we live in the northern hemisphere, we go out and we look at the sun, regardless of the time of year, the sun is always tilted towards the southern side of the sky. So even in the height of summer, the sun still has a little bit of a tilt towards the south, and especially in the winter, you can really tell that the sun is always in the southern direction. But I think it would be very jarring to go to the southern hemisphere and then it would be the opposite. It would be the sun would be towards the northern horizon. Because I think that would be very jarring for me, because I use it as wayfinding. When I'm like walking around, if I'm hiking or something, I look for where the sun is, and I can, because I know that the sun is always in the southern direction, or I know that the sun is rising. It rises in the east, it sets in the west. I use it for wayfinding, and the fact that it is always in the south really helps me with that. So I feel like it'd probably be very jarring to be in the south and have that to be the northern direction. Everything's backwards and upside down there. So it'd be fun to experience.
One of the weird things that happens too, and in the last stream that we did on Friday, Monica, who lives in Australia, pointed out that she was actually asking the question of why the moon is backwards. Like the crescent of the moon is opposite to the way it is in the northern hemisphere. And that's the exact same thing. The answer that I gave her was basically that we're upside down from you in Australia. You are standing literally upside down from the way we're standing. And so you see the moon's crescent as being backwards, which is really strange and would be kind of weird.
Imagine like Monica in Australia, her head would be like facing like down this way, and your head would be like pointing up that way. And if you brought your feet right together through the earth, you'd be literally facing, like your heads would be pointing opposite directions, and you'd be looking at the same thing out in space from a different angle. It's wild.
It's the perspective that really messes with you, right? So that's I always found that a really interesting one. And here's the thing too, is that if you're at the equator, the phases of the moon actually happen evenly. So like a first quarter moon, the barrier, the terminator between the light part of the moon and the dark part of the moon is literally in the middle. And it's flat, parallel to the horizon, which is kind of crazy.
Oh, that's interesting.
Yeah, right?
Of course it would be. I didn't even think about that. That's awesome. Thanks for telling me about that.
Because it's kind of in between, so yeah, kind of funny.
Yeah.
Anyway, so that's the seasons. We are Jen in the chat.
And we just passed the equinox, of course, right?
Oh, yep.
We just passed the equinox, so we're now officially into the spring months, and the days are growing longer and longer. But when we say equinox, it means that for that one point at the equinox is when we the Earth was neither tilted toward or away from the sun. So at that one point on March, I think it was March 20th or March 19th, mm-hmm. At that one point, the Earth was neither tilted away or towards, and so we were right in the middle. And now we're slowly tilting towards, and I'm of course looking forward to this, because that means summer weather and no more of this winter business. And those
poor Aussies just getting into their winter. Although I'm not really, I don't feel that bad for them, because Aussie winter is still pretty comfortable. So I'm going to say that they're doing pretty well.
Yeah,
no matter
I don't
what.
even know what Aussie winter is. Yeah.
I think it's like autumn here.
Anyway, have no idea.
Yeah, so the thing that I wanted to ask you, Jesse, is your expertise is actually in quasars, which is
yes.
Which I do know what they are. I'm not going to go and steal your whole explanation. I'm going to pretend to be really smart and say that I know everything about them, but that I'm getting you to tell us all about quasars. So I'm kind of excited because so for those who don't know, Jesse has his PhD, and his PhD work was on these really fascinating objects that we call quasars, and probably a bunch of other stuff that was all rolled into one PhD. But so I'm gonna let you go ahead and explain what is a quasar, why are they weird, and that this will be a little bit more advanced than some of the topic that we cover, but we switch between some advanced stuff and some straightforward stuff. And
it's not that advanced.
No, well, you're good at explaining it. You're good at bringing it to the right level.
It's a really fun topic. So hi everybody. I did my PhD at York University in Toronto, and I had a really great time studying. I studied quasars. Quasars are a subset of a thing called active galactic nuclei. So in the name active galactic nuclei, it has everything you need to know about it. Now I'm gonna share my screen with you, and I think
so. It's active. It's a galaxy, and it's nuclear. It's a nucleus. Look at that, all the stream back end too. Everything's up there.
Okay, can you see this?
I can see that. It looks good.
It's
a beautiful
it's a galaxy.
Yeah,
you see it?
Very nice.
Okay, sweet. All right, so that is that's a galaxy right there. That's a I'm actually not sure if that's an artist impression or not. I can't remember where I got that from. I mean, I know the credit is down there, but I can't remember if it is an actual image or an artist impression. But nonetheless, the point here is this is a disk galaxy. It's much like the Milky Way. The Milky Way is a disk galaxy, so it's flat like a pancake, and it's round like a pancake. So it's, and I have dimensions here. So our galaxy, the Milky Way, is about 35,000 parsecs in width, in diameter, across the circle that is the disk of the Milky Way. And we live about 2/3 of the way out from the center. So we're somewhat far out. Like the center is very dense, and you can kind of imagine, if you're thinking of it like a city, the center is kind of like the downtown core, and way out at the edges of the circle would be the rural parts of the city that you live in. And we live sort of in suburbs. I would say the sun lives in the suburbs of the Milky Way. And galaxies like this, major galaxies like the Milky Way, they have hundreds of billions of stars. They have hundreds of billions of planets, or like most stars have planets. They have gas, they have dust, they have a whole lot going on, and they have a whole bunch of black holes. A black hole is an object that is so massive and so dense that light can't even escape it. So we understand gravity pretty well. Gravity is the thing that keeps us sitting in our chairs right now. But on a black hole has so much gravity that not only would it be impossible for you to escape, but it's impossible for light to escape. And that's why we call it a black hole. Now there's millions of black holes throughout the Milky Way, but they're all about 10, 20, or 30 times the mass of the sun, maybe even 100 times the mass of the sun. So I say that to me, that's small. That's a small mass black hole.
Yeah, to me too.
Times the mass of the sun.
Oh, I mean, to anybody who's hearing that sounds pretty big, pretty massive. But you're right. It is relatively small as far as some black holes go.
Yeah, from a black hole perspective, it's a small mass, because I study supermassive black holes, and the cool thing is that that's an actual scientific term. Supermassive black hole is an actual scientific term for a class of black hole that is millions or billions of times the mass of the sun. So in every major galaxy, there's only one of those. There's millions of little ones and one big one, and that one sits right there at the center of the galaxy. We have one. It's called Sagittarius A star, and at the center, it lives at the center, and it's the only supermassive black hole that we know of in our galaxy. And any other major galaxy you look at is going to have one. Now, there's two types of supermassive black holes at the center. They can either be active or quiescent. And when I say these two words, I mean active means that it's actively eating. It's actually pulling stuff in, like it's eating, stars that have gotten too close, gas and dust and stuff.
So dinner time.
Quiescent, which means literally it's doing nothing. Yeah, dinner time. That's right. Quiescent is like quiet. It's like it's not doing anything. It's just sitting there.
So loud or quiet?
Supermassive black hole. Okay. Quiet? Hey.
Loud or quiet, basically, are the two options.
Mm-hmm.
Okay.
Loud or quiet. That's right.
There's not really anything in between. There's not really anything in the middle.
That is a good question. I think that the efficiency of accretion, so the ability for a black hole to eat material, is pretty sharp. So I think it's what I mean by that is it can actively eat really easily for a while, but if enough stuff gets piled up there, then it will it won't all be able to fall on at once, and so it'll kind of immediately turn into an active nuclei.
Oh, okay, interesting.
So let's zoom in. I'm going to zoom into the center here, and just to remember scale here. There we go. 35,000 parsecs is the width of this galaxy, the diameter. And if we zoom in on the center to an active black hole, it would
Whoa.
look something like this. And I got a cool video. Check this out.
That is very cool. I'm seeing just the image, and it's pretty cool.
Yeah, the video doesn't seem to be coming from me.
That's okay. That image is pretty neat.
And that would be about the size of the solar system. That image. So it's much smaller than the galaxy, and it's a whole bunch of material, a whole bunch of gas and dust. Oh, there it goes. That's
it decided to like you.
The black hole. It's
wow.
It's almost like, imagine like it's a bunch of, like, you know when you like pull a drain on a bathtub or pull a drain on a sink or something, and the water all wants to go down the hole, but it can't go all down the hole at once, so it creates a whirlpool and it circles the drain.
Oh, interesting.
This
okay.
is kind of like what's happening at a black hole.
Wow.
And that entire thing is called a quasar, an active galactic nucleus.
A super hungry black hole. Super hungry black hole.
Hungry black hole, exactly.
That's pretty awesome.
And I might be back. Can you see me now?
Yeah, we can we'll bring up the Ryan and Jesse cam to make sure that you're still there and you're looking good and everything. Awesome. That was great. Thank you for that. So that was what you did a lot of work on and got your PhD because of all that hard work.
It went on. It definitely went on for a while, but it was hard, but it was fun. What I did with my supervisor is we took images of the same supermassive black holes over and over and over again, because we wanted to see how that disk of material changed through time.
Oh, neat.
Over a period of like 10 years. So it was cool. We saw some really interesting changes, and one of the things I can tell you that we saw was that it was almost impossible to predict the changes that would happen. We really tried to attempt to predict how a quasar would change through time, and it didn't seem very easy to do based on our data.
Whoa, that's pretty amazing. I mean, it's just cool to get to look at something over a period of 10 years and see what it does and what it's doing and how it's changing, especially something so powerful that it's kind of at the edge of the laws of physics too, right? Like there's things happening there that are really tough to explain and to predict, and even when you do see them and do predict them correctly, it's still tough to ensure that you're going to be able to predict it even more in the future.
Oh, the reason I studied quasars, the reason I was interested in it, was because they're like the most extreme thing in the universe. Like, it's millions or billions of times a mass black hole with a whole bunch of stuff falling on, and it's hot. Like, the temperatures there are hot enough, like millions of degrees, like super hot in that disk that's swirling the drain. They create so much energy that not only are they really far away, they're more than halfway across the universe. Most quasars live about halfway across the universe. We can still see them quite easily with relatively small telescopes. In fact, even with a small one, like a 30 centimeter or 60 centimeter telescope, you can pick up a few quasars in that thing, because
Really?
they're so damn bright and their light gets all the way across the universe to us. So I was just super interested in studying them because they were so extreme.
Do you think that that because there are very distant galaxies that are quasars, that it enables us to see these galaxies when we otherwise wouldn't be able to?
Oh, definitely. Yeah. Yes. In many cases, the quasar outshines the entire galaxy. So imagine a galaxy with hundreds of billions of stars and one quasar right at the center of one supermassive black hole that's actively eating.
Yep.
That all of those, the collective shine of 100 billion stars is not enough to outshine the light from the disk around a quasar. It's insane. Like, if the quasar wasn't there, we may not be able to see the galaxy at all. Absolutely.
Wow, that's pretty fantastic. Jesse, to try and get
crazy stuff. I don't do that anymore, though.
Oh no. Now you do a lot more communication stuff, but you're having fun with it. And that's what matters.
Yeah, now I work at the Canada Aviation and Space Museum, and my job is to to educate. I work with the exhibits we build. I work with programming that we do at the museum. I do a lot of like blogging and social media to communicate interesting sciences. So now it's much more science communication, education, public outreach, and working with the public. It's a lot of fun.
Well, as long as you're having fun, that's what's important, right? That's the dream.
I know, man. I am.
That's the dream. I do, yeah. I love hearing about all the fun things that you're working on and that you're doing. So we do have one question in the chat from the seasons bit from Carlo Berardi.
Oh yeah.
And it was, why does the Earth tilt? Why does the Earth tilt, Jesse? Why does the Earth have a tilt?
Probably from an impact. I mean, it's really hard to say.
Yeah, specifically.
So it probably goes back. Like, it could have been a lot of things. Impact is probably the most likely scenario, but it also could be massive shifts in like, if you have a lot of liquid added to the surface of water, like a lot of water was, say, came up onto the surface of the Earth, it could shift the mass distribution on the Earth. But it's probably related to impact, wouldn't you say?
Yeah, most likely. I mean, in the early solar system, there was so much stuff going on. There were so many things flying around, right? Like, you had the sun formed, and all these other bits of dust and gas were collecting into rocks, and those rocks were collecting into boulders, and the boulders were collecting into mountains, and the mountains into planets. And so you had all this stuff flying around, smashing into everything, and basically that's when it happened. It's really, I think, more rare for a planet to form nice and flat and straight and even than it is for a planet to form when it's getting bombarded by things that tilt it, that turn it. You know, there's two planets that I can think of that are far more tilted than the Earth, right? One is Venus, which was likely hit so hard that it's actually spinning backwards right now. And the other is the planet Uranus, which is tilted 90 degrees. So its North Pole is facing the sun, right? Which is a really strange thing. So I look at the Earth and say that that's not that tilted compared to some other planets. And for reference, Mars's tilt is actually pretty close to the Earth as well. So maybe it had something to do with the fact that where Earth and Mars are, there was a certain amount of impact that led to just a little bit of tilt, not a lot. You know what I mean? So kind of neat.
And I also have to think that, like, you know, when you start with a spherical gas cloud, right?
Yeah.
So the solar system started spherical, and it as it spins and stuff is falling into the star that's growing at the center, which becomes the sun eventually. As it spins, it flattens out into a disk, and because that's just what happens with angular momentum. You spin fast enough and it flattens, and then you have this disk of material that's all orbiting the sun. But that disk of material isn't perfect. It's not a perfectly flat thing, and not everything in it is perfectly going the right direction. So you have random chance. You have random angles in your formation of what we call a protoplanetary disk. As the disk settles into a flat disk, you have lots of different things smashing off of each other, and it's not all perfectly in the same plane. So you're gonna get random tilts. Like you said, it's unlikely that you'll have everything perfectly perpendicular, all lined up parallel along all north-south axis of all planets in the star, all parallel and perpendicular to the plane. That's very unlikely.
So the big question then is, did our solar system form in a normal way, so that when we look at other planets around other stars, are they forming the same way our solar system did, or is ours very unique in the way it formed? And that is a tough question that we'll probably leave for another time, because it is, we could dive pretty deep on how other planets form, but we are going to talk about some other planets as well. I want to actually take us to a program that I marked in the first comment, because we have another question from Diane in the chat about ocean tides. I know there's some connection to the moon. Can you explain ocean tides? We're going to do our best. So we're going to start with this lovely program.
What, you don't know the answer to this?
Oh, I do. But whether I can explain it or not is a whole other story. So I'm going to bring up this lovely little program that we call Universe Sandbox. And this I've been using a lot lately, and I'm really glad to use it for the stream, because it lets us kind of play around a little bit with the Earth and the Moon. Now, this is not to scale in terms of distance, the moon is the right size. So this is about how big the moon is compared to the Earth. It's about a quarter of the size. And the idea with tides is that there's this thing called the tidal force. It's really the difference in gravity from one side of an object to the other. So let's think about the moon for a second. If we look at this side of the moon, the right side of the moon feels more pull from the Earth's gravity than the left side, because the left side is just farther away, right? The side that's facing Earth just feels more pull than the side that's facing away from Earth. And it's that difference in gravity that creates the tidal force. Now the Earth does that to the moon, but the moon also does that to the Earth. So the moon's gravity also depends on how close the Earth is to it. And because the Earth is quite a bit wider, we can see on the left side of Earth, the side that's facing the moon, it's a lot closer to the moon than the far side. Now this is, of course, exaggerated, right? The moon is in reality much further away. But what this does is the side of the Earth that's facing the moon, the water on the Earth responds to that extra pull. And so more of the water is trying to get over toward the moon, moving to the side of the Earth where the moon is. And that creates your high tide. Now the effect also does something that's a little bit tougher to explain without a little bit of vector addition, so I'm not going to dive into that right now. But basically, not only do you get the effect on the side that's facing the moon, you get the same effect on the opposite side. So basically what's happening is you have a high tide on the side of the Earth facing the moon and the side that's facing opposite to the moon. And because the Earth turns every 24 hours, if you imagine one point on Earth, right, if we move this forward, now we're going to start to get all kinds of crazy stuff happening. I'm going to ignore that for now. But what happens is as the Earth turns...
The moon is falling apart.
I know, right? As the Earth turns, every 6 hours, the Earth kind of switches. It goes from those points are high tides facing the moon to those points are low tides not facing the moon, and then to high tide and low tide again. So we have high tide and low tide twice a day for that reason. Jesse, is there anything you want to add to that explanation? Because that's really the best I've got.
No, that's good. I mean, you nailed it. There's two things, right? So you have the sun involved as well. So the sun, sometimes you can have the moon and the sun line up in the same direction, and that amplifies the effect because the Earth can feel the gravity from the sun as well. And so you'll have an even higher tide than normal. And then sometimes the Earth and the moon and the sun are at right angles. So the moon is one direction and then the sun is the other direction. And when that's happening, the tides are not as strong. So you'd have a weaker tide. And then the only other part to that would be the reason you have it on the other side. It is tough to explain. I try to explain it when you say, obviously the side facing the moon it's easy to understand that because the moon is close to it and it's pulling the water.
Yeah.
But you have to also remember that it's pulling the entire Earth. And so if you go to the far side of the Earth, on the opposite side to where the moon is, then the top of the ocean on that side is further away from the moon than the bottom of the ocean. And so the bottom of the ocean is being pulled towards the moon a bit, and the top of the ocean on that side is not quite as pulled as hard, and so it stretches out a bit, gives you a high tide on that side. I don't know if that's how I explain it. I don't know if that's easy to understand though.
I think it is. I'm pretty happy with that explanation, considering we didn't have this prepared. This is the fun thing about doing questions out of the chat, is that it's really nice to be able to answer them. But it's a lower production value than the things that we plan to talk about, right? So this is one of those things where, what we'll probably end up doing is we'll take a couple of these questions, and then the next time I do a stream, I'll answer them again with a bit better production value, right? So we do our best right now, and we go from there. We just got a lovely thank you in the chat from Carlo for answering the question of why does the Earth tilt. So there you go. See, it's worth it, right? The next thing,
Carlo.
Yeah, right. The next thing I do want to talk about is Comet, because in the news we've got. Oh, and thanks, Diane says the good explanation. It makes total sense. I'll take it. Total sense is always the goal, right? So the next thing we're going to talk about is a comet, because this is actually a really exciting time for astronomy right now, and I'm going to bring up both of us, Jesse, so we can talk about
all
this.
The times are exciting times for astronomy.
It's true. There's always something really fun happening in space at any given time, but this is a really interesting thing. We actually have a comet that's moving moving close to the Earth and closer to the Sun. It's in our solar system. Comets tend to be visitors. They don't tend to stay for too long, and so this particular comet is getting brighter and brighter faster than we're expecting it to. And what that means is that in about a month and a half or so, it's actually going to be bright enough to see with just your eyes in the sky, which is really exciting, because if anybody here has not seen a comet in real life before, it is a spectacular looking object. And the amazing thing is
have you seen a comet in real life?
Yes, one comet.
What?
And it wasn't even a nice
see?
It wasn't even a really nice one. It wasn't like Halley's comet. It wasn't, which was, in 1988 when you and I were like 3 years old. It wasn't Hale-Bopp, which was a very famous comet from 1997. The comet that I saw was called it was a Pan-STARRS comet in it must have been about 5 or 6 years ago, and I had my little telescope and I saw it. It was barely visible to the naked eye. But it was a really cool thing because you could see it there with the tail and everything, and it gave you this sense that it was actually moving, right? Because the tail does that. So
that's cool.
I'm going to bring up the Universe Sandbox stream because I just want to show a comet here. This is basically what a comet is. It's a big dirty snowball, and this particular comet is...
Yeah, it doesn't look like much, Ryan.
No, it doesn't. It's 5.5 kilometers wide. This comet, 5.5 kilometers wide, so pretty big. It kind of looks like a big snowball. The way I
could run that in 40 minutes.
Oh yeah, totally.
So you could run the diameter of it. Lots of us can run a 5K, right? Or at least walk a 5K.
Some of us can pretend to run a 5K, Jesse.
I mean, we can all handle that. Just you can picture 5 kilometers in your head, right? It's not that big.
No, it's really not. It is imaginable. But so you can run it in 5. But what I wanted to say about this particular comet, and the way I like to explain comets, is that it's like the snow that you find in March. That snow that's kind of starting to melt, and it's covered in dirt and sand from the sanders. And if you took that and it's slushy and you tried to make that into a snowball, a comet is basically what you would get. Comets also have a lot of what's called ammonia, that spits out of it, and some other organic molecules kicking around. So a lot of fun things that make up the soup of comets. But this particular comet, I'm going to bring up our browser because there's a website that I posted earlier on that talks a little bit about this comet, and I'm going to start up here. This image that you can see, the comet's name, by the way, is C2019 Y4 Atlas, or just call it Comet Atlas colloquially. It's a little bit easier to understand. And so
I'm never going to remember the other name.
Well, there you go. I mean, C2019 when it was discovered, Y4 is a designation based on how many comets were discovered this year, and then Atlas was its colloquial name, usually named after a telescope or survey that discovers it. So one of the things you can see just in this little simulation here is you can see the orbit of the comet. This is kind of where it is right now, right about here. You can see the Earth, Venus, Mercury, the Sun. You can kind of see above the solar system. We see the comet is kind of working its way right through the solar system over time. It's going to take a couple of months to get there. Its perihelion, if you see up here, is May 31st, which is its closest point to the Sun. It's also going to reach a magnitude of -1.6, which is really bright. That's
yikes,
brighter than most of the stars in the sky. Okay, so that's a big thing.
That's the only thing brighter than that is Venus, right?
Yes, and maybe probably the International Space Station as well. But we talked about that on Friday, and we saw how bright the ISS was. This is a really bright comet. And if we actually scroll down a little bit, this is a really important plot right here. What we've got, this is the magnitude of the comet over time, the brightness of the comet over time. And you've got this curve here that kind of shows what we expect it to do, how bright we expect it to get in the minimum and the maximum. And the dots are showing what it's actually doing. So you can see that already, as we're here at the end of March, early April, this comet is brighter than we're expecting it to be right now. Now, one of two things could happen. Either it could keep going on this trend and get super bright and be like the most amazing comet in the past 20 years, or it could peter out and go below the curve and still be kind of cool, but not as spectacular as we all hope. And the really tough thing about it is that comets are super unpredictable. The reason that we can see comets in the sky is that as they get closer to the sun heats up their icy surface, starts pockets of gas exploding off of that surface, dust falls off, and it creates two tails that we see on a comet. But it's very hard to predict what the comet is going to do, how bright it's going to be, how reflective its surface is, because comets are not all exactly the same. Some have more ice, some have more dust, some have more dirt, some have more ammonia and organic molecules. So it kind of goes all over the place.
Some are more tightly packed, or some are loosely packed.
Exactly, right? And so all these properties go into how bright a comet is going to get. And there's been many famous examples of comets that we thought were going to be spectacular that ended up being kind of dull and not really going anywhere. The closest one that I can remember is Comet Ison from about 10 years ago, where we were expecting it to be like the brightest comet of the century. Yeah. And all year we watched it, we kept an eye on it. And the comet went behind the sun and it never came out. It disintegrated when it went close enough to the sun, and we never saw and that was the end of it. So it was just never really good to see at all, which is kind of a bummer. So
went to the sun and was never seen again.
Basically. So hopefully this one's a little bit better. And the next chart you can see here gives a showing of where it's going to be, constellation wise. So right now, it's kind of, this is the Big Dipper right here. You can just kind of see there, and that was on March 1st. April 1st, tomorrow, it's heading over a little bit. Trying to see the constellation. This is Draco right here, and then this is, I think, Cepheus. Yeah, Cepheus over here. So
I think it's heading in that direction. Yeah.
So kind of off the spoon of the Big Dipper, that comet's kind of working its way over the course of the month. And there's a lot of great animations online showing the movement of the comet over a few hours, because when you have a big telescope and you zoom right in on it, it looks pretty spectacular. So we'll go back to Universe Sandbox, and we can show kind of what a comet looks like again. This particular comet that I've shown here is a simulation of what Halley's Comet actually looks like. So it's 1P Halley, which is kind of interesting. Halley's Comet about 5.5 kilometers across. But Halley's Comet, nice and predictable, so that certainly simplifies things a little bit for us. Jesse, anything you want to add about comets in general?
It's on an 80-year orbit?
Yeah, 76. Yeah, 76 years.
Halley's Comet, when's it coming back?
Not for a while. I think it's 20... So I think 1988 was the last time that we saw Halley's Comet.
2061.
So that would have been 1984. Yeah.
1986.
Oh,
1986 was the last one, and then
so apparently I can't math.
It'll be coming through our skies again in 2061. So how old are we going to be, Brian, in 2061?
Can we not think about that? I don't know.
What we know for sure is that
70s.
it'll be a good show in 2061. That's what we know.
It will, and I'm really hoping that Comet Atlas is much better than Halley's Comet, so that we can say, well, we were there when Comet Atlas happened, and then we don't, and then it's like, oh, Halley's Comet,
yeah,
okay, I guess
a tall order, though.
That's pretty cool. So it is a tall order, but when we're really old and we're saying to kids and grandkids like, oh man, you think Halley's Comet is something? You should have seen Comet Atlas. That's what I'm hoping for.
Way back in 2020, we saw a comet way better than Comet Halley.
Yeah, right? There you go. So that's comets in a nutshell, and I posted that link in the comments to the stream, so you can find it there, and we can talk about that a little bit more if anybody has any questions about it. But now I'm gonna pull up some really fun stuff for the last little bit of the show. We got about 15 minutes left. We're doing pretty well. I want to talk a little bit.
Save the best for last.
Well, I think we started with the best, Jesse, and that was you slightly after the beginning. So. We started with the best.
That's true. Yeah, that's true.
And we're moving to the filler stuff, right? That's we're moving to the stuff that's a little less exciting. But the reason I'm bringing up this Universe Sandbox thing is that it's really fun. I really enjoy the software, and I've had a lot of fun kind of playing around with it. So, you know, it's neat for simulating interactions of objects throughout the universe. I have posted a link to where you can get this program in the comments, but I'm not affiliated with them or anything. It's really just me doing this for fun, and I think it's a really neat program and that more people should use it. So let's have some fun with Universe Sandbox. The first thing I'm going to do is actually bring up the Earth, because we can just add the Earth.
Let's do the Big Bang.
Let's do the Big Bang? I don't think we can do that.
Yeah, let's just start from first principles.
Oh,
let's just go right to the beginning.
In the beginning. No, okay. So we've got the Earth here. It's a really nice view of the Earth. What I want to use this for is comparing the sizes of some things. And one of the first things we can compare the Earth to, of course, is the Moon. Now we're going to start it without moving so that it doesn't go anywhere or cause any damage or anything. But you can see the Moon about this large compared to the Earth, about a quarter to a third of the size. I'll just move a little bit closer there, try and get a better view. And you can see this is about how big the Moon is, but it's not this close. The Moon is actually quite far away, and if I can show you just how far away it is, the average distance is about 384,000 kilometers. So we're going to have to keep going and going and going. There we go. That's about 384,000 kilometers right there.
Whoa.
So focus on the Moon, you can see that distance. We focus on the Earth, see it a little bit there too. So pretty far apart. Zoom in a little bit. It's about 30 times the diameter of the Earth is the distance between the Earth and the Moon. Okay, but we're here to talk a little bit more about the sizes of things, so we're going to bring the Moon back, and we can see it there. The next thing we're going to add is a planet. Jesse, pick a planet. Any planet.
Mars.
Good choice. That's what I would have picked too. So here's Mars.
Mars is the best. Mars
is pretty awesome. We're going to bring up Mars, and you can kind of see how large Mars is compared to the Earth there. We're just going to fix the lighting a bit, but you can see Mars a lot redder than the Earth, the rusty red Mars, caused by iron oxide in the soil. And we can see that...
Which you can also find in Prince Edward Island.
Oh yeah, same stuff, eh? Isn't that clay in the soil?
Yeah, iron oxide.
Really?
Well, it's rusty colors, and yeah, it's all over the Earth in various places.
Cool. So yeah, there's Mars. One of the confusing things about Mars is that we often think of it as being similar to Earth in size, in shape, and it's the closest thing to Earth. It's like Earth. Mars would have been a lot like Earth hundreds of millions of years ago. But one of the first things to wrap your head around is the fact that Mars is quite a bit smaller than the Earth. All right, so let's add a gas giant. How about Jupiter? And let's see how large Jupiter is. Quite a bit bigger, but we'll move it pretty close so we can see Jupiter there. Now we're getting into the gas giants. Jupiter is the largest planet in the solar system. About 1,300 Earths would fit into Jupiter, which is pretty amazing. And if we kind of
one of my favorite facts about Jupiter is that yes, it's the most massive one, but not only is it the most massive planet in our solar system, if you added up literally all the other planets from like Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, Pluto, all of their moons, if you added up all of the material in the asteroid belt, you still wouldn't meet the mass of Jupiter. Jupiter is bigger than all of the planets combined in our solar system. It's more massive than all of the planets combined. It's insane.
That's pretty amazing. And then another factor on that is that the sun is more massive than all the planets, including Jupiter and all the other stuff.
Yeah.
By a lot. So, but that's pretty awesome. I like that fact. One of the things you notice too is the Great Red Spot, which is a giant hurricane on the surface of Jupiter. Earth is about 2 Earths would fit into that giant storm, which is pretty amazing. Question in the chat from James. Thank you. How much time does it take for landers to reach the Moon and Mars? Well, for the Moon...
Ooh, good question.
The Moon... I'll do the Moon part, and Jesse, I want you to do the Mars part. The moon is about 3 days away by rocket ship. When the Apollo 11 astronauts went to the moon, it took them about 3 days to get from the Earth to the moon, 384,000 kilometers. Mars is much further away, though. Spaceships today can go a little bit faster, and especially when there's no people on them, it's easier for a lander or an orbiter to reach a body like the moon, and so it still takes a couple of days, but a lot faster than to another planet. So Jesse, how about Mars?
Mars is like 6 to 8 months of travel time, because you have to, it's with the moon, it's so close to us, it's 384,000 kilometers away. Mars, it's at our closest approaches to each other, it's something like 75 million kilometers away, but you can't do a straight shot at it. You have to do a matching orbit, so you have to literally travel hundreds of millions of kilometers to reach the planet and to get into orbit around it. So it's 6 to 8 months travel time to get there.
Yeah, and actually I'm going to just bring up a quick thing on the solar system, so you can kind of see if we pause here for a sec. So here's the Earth, and if we zoom right in, really far in, okay, there's the size of the Earth. We zoom back out, you can just see just how crazy far away Mars is over here. And you can see that because their orbits, like you were saying, Jesse, you have to match the orbit. If you leave the Earth, you're going to start flying around the sun, and your goal is to try and hit Mars at just the right spot, just the right time, just the right date. And we can calculate that pretty easily. And so it's even with that calculation, it still takes that 6 to 8 months, as you were saying, to get all the way from Earth to Mars. And that's one way. So when we do send astronauts to Mars, it's 6 to 8 months there. Hopefully the astronauts will want to stay for a while, and then it's another 6 to 8 months all the way back.
And you have to really worry about where they are in their orbits. So there is an optimal time to fly to Mars, and it happens once every 2 years or so. And so, and then there's an optimal time to come back to Earth, and so you have to factor all of that in to your travel time. The moon is a lot easier because the moon is right out there, and it's super easy to get to and come back from. And that's why the next missions, like the next human missions, will be to the moon first, and then back out and then hopefully out to Mars after that.
Yeah, the moon makes a good outpost as well. Here's the size of Saturn as well without its rings. Also pretty big, a gas giant. But now we're going to get into some stars. I'm going to bring up our favorite star, the one that gives us warmth and life and all those good things. This is how big the sun is.
Raw.
It's bright, it's hot, it's big, and there it is. There's the sun. Pretty powerful. You can see it compared to the Earth. 1 million Earths can fit within the sun. 1 million Earths. 1.3 million, actually. Which is pretty insane.
That's a lot. I did not know that number.
Yeah, right? It's pretty amazing to think about. And yet, we can see it here, and it's kind of like, oh, there's the Earth, and there's Saturn, there's the sun. Well, the sun is actually a pretty average star. Jesse, question for you. What is the brightest star in the night sky?
Come on, I thought you were going to give me a hard one, Ryan. That's obviously Sirius.
I can make them harder. All right, let's bring up Sirius then.
Okay, you probably know a lot more about the night sky than I do. I think you can stump me pretty easily.
I don't know about that. Well, there's Sirius, and Sirius is a very serious star, right? I have to make terrible jokes at least once, but it's big, it's bright, it's a white star, so it's hotter. It means it has a hotter surface temperature than the sun. White stars are around that 10,000 to 12,000 degree mark, and blue stars are even hotter than that, up to 30,000 degrees. Whereas our sun's about 5,500, kind of decent temperature there. So, but Sirius is a little bit bigger.
Sirius is also one of the best characters in Harry Potter.
Yeah, definitely. I would say so. Right? And I always I have to laugh because every time I do a planetarium show and I'm like pointing out Sirius, you hear all the kids and they're like, oh yeah, it was Harry Potter, yeah. And I'm like, oh yeah, and over here is Hermione, and that star's Harry Potter, and this one's that, and we just run with the joke for a little bit, and they're like, really? I'm like, yeah, no. But that's okay. It's fun.
No.
A lot of the characters came from stars and objects in the night sky. But one of the things I like to talk about with Sirius is that even though it's not a very big star, the reason that it's the brightest star in the night sky is that it's relatively close to us. It's about 8.5 light years away from the sun, which sounds like a really long distance, but is actually, compared to other stars, is really close. All right, we're going to add one more. Here's one that's a bit tougher, Jess. What star visible in the night sky with just your eyes is the largest star? In the winter sky,
okay.
I'm going to say.
Visible to the eye, and it's in the night sky. I would say Betelgeuse.
You are correct. It is.
Yes.
It is in fact Betelgeuse. So we're going to bring up Betelgeuse, and you can see already it zooms us right out. We'll put it right.
Don't say it 3 times, Ryan.
Okay. No, if you say it correctly, it's Betelgeuse.
Betelgeuse.
And look, here we are.
Not Beetlejuice.
Right. So here's the sun, and right next to it is that massive star, Betelgeuse. I think about 1 billion suns, maybe not 1 billion, maybe 100 million of them would fit into Betelgeuse. Much bigger star, but in the sky, it's actually about 630 light years away. And so it's much further away than Sirius is, so it looks less bright, but not by a lot. Betelgeuse has been in the news a lot lately because we've been talking about how it might explode as a supernova anytime within the next 1,000,000 years. But that's still 1,000,000 years from now, so we don't have to worry about it too much. But I do have a little video of Betelgeuse that I've wanted to show for a while. This is actually a numerical simulation done by an astronomer to show what the surface of Betelgeuse is doing. Now the thing is that the reason that there was a lot of news about Betelgeuse in the past few months is that it started to get dimmer unexpectedly. And when a star gets dimmer unexpectedly, it could mean that it's collapsing into the supernova. Sorry, I'm just trying to find my video here. Where is that?
I see a picture of Betelgeuse.
Well, that's good.
Or at least a simulation of Betelgeuse.
Okay, well, that's a start. I'm actually going to try and play it. There we go. That's what I'm hoping for. So you can see, so it was getting dimmer, and so people thought, oh, well, maybe that means it's going to explode any time now. And then after a month or so, it started to get brighter again. It is a variable star, and if you look at that video, you can see that the surface of it is boiling. It's roiling, kind of like boiling water. And so, of course, it's going to get brighter and dimmer as it goes through this process. It doesn't necessarily mean that it's getting ready to explode as a supernova. It still might, but it probably isn't going to happen tomorrow. And now that I say that, it's going to happen tomorrow. Right? Right.
Well, that would be pretty damn cool.
That would be really cool.
Because if it did, a supernova, so it's 600 light years away, which is far, but from a supernova point of view, supernovas are the brightest thing in the universe. Like that kind of explosion, it tears apart stars and can create black holes. So it's a very energetic process, and something like that, if Betelgeuse did supernova, it would be visible in the night sky. It would be like almost as bright as the full moon. It would be a very, very noticeable thing to happen. And something similar to that happened back in, when was it, Ryan? 16-something.
Are you thinking of
1680 something? Oh, I can't remember.
Of Kepler's supernova or Tycho Brahe's supernova?
Was that the one? Something like that.
Yeah.
I can't remember. Yeah, Kepler's nova. Yeah, Kepler supernova. I think that was the last one that was in our galaxy that we know of.
Yeah, correct. There's 1987.
It was super bright.
But that was in the Large Magellanic Cloud, which is a galaxy that orbits the Milky Way.
Right.
I'm going to bring up one more star. This is the largest known star in the universe. This is called...
Oh my gosh.
UY Scuti.
Is it... I was going to say, is it VY Canis Majoris? Or is... Yeah, there's a new one.
Yeah, VY Canis Majoris is second. And I'll add VY as well. So here's... I know it's a lot of light going on here, but there's VY. There's Betelgeuse. and there's UY Scuti, which is even larger.
Oh my gosh.
The thing is that these stars are called red supergiants. You actually can't get stars much bigger than this. Because if you do, they literally just collapse in on themselves and become a black hole. They blow themselves apart. A star is basically a balance of pressure pushing outward and gravity pulling inward, right? And so the bigger a star is, the more energy it has pushing outward. And these stars are not a lot heavier than the sun. I mean, if you look at Betelgeuse is about 12 times the mass of the sun, which you would think is a lot, but it's not really compared to how much bigger it is, right? It's 100 million times as big as the sun, and yet it's only 12 times as massive. So there's a lot more energy, a lot more pressure, a lot more power pushing outward than there is gravity pulling inward. And that's why when we look back at this image, we can see Betelgeuse kind of boiling and going crazy, because there's so much outward pressure from its nuclear engine that it's barely holding itself together. So stars bigger than this tend to literally blow themselves apart.
Yeah, they're very billowy. They're very not dense. It's a lot of mass spread out. It is a lot of mass, but it's not that much mass. But it's spread over a very large volume, and they kind of the way I remember being back in undergrad, and Alison Sills told me that you can kind of think of a red supergiant like a marshmallow, and a little white dwarf would be like a bullet, like a hard stone. So you can see the difference, right? A marshmallow is sort of billowy and it's not very dense, and it's sort of fluffy and cloudy, whereas a bullet or a rock is very dense and hard, and those would be the smaller stars, the more dense stars.
Well, I'm glad you said that, because we can actually add a white dwarf. And here's
that was what I don't know if you remember, my undergrad thesis was we collided red supergiants. We simulated collisions between red supergiants and white dwarfs.
Oh, that's cool. So here is the white dwarf, though. Sirius B is a small dwarf star that orbits Sirius, and if we compare that to the Earth, look at that. It's about the same size as the Earth. Yeah, this is a star.
That's crazy.
This is a star that weighs 1,000 times as much as Jupiter. And yet,
oh boy,
it's packed in. So it's very, very dense. That's a white dwarf star for you. We have a question in the chat.
Oh, there's a question in...
You seeing it too?
You got to it at the same time as me.
Yeah, right on. See, that's good. See, it means this is 15 years of working together, Jesse. This is what has happened. Is we just read each other's minds about what we're talking about. So this will be probably our last question for the night, as we're getting to past the top of the hour. It's from Vineet Honkin. If Betelgeuse went supernova, would it affect the Earth physically? What do you think?
No.
A very concise answer. He's a man of few words.
Yeah.
You're correct. It probably,
it's too far away.
Yeah, it probably wouldn't. So Vineet, if Betelgeuse goes supernova, the worst thing that's going to happen is nighttime will be really, really bright for a couple of weeks. For about 2 weeks, we'll be able to see this star explode in the daytime. It'll be like having a second sun that's just not as bright as the sun, and then at night it will just light up the whole sky and be kind of cool, and everybody will get to see it and enjoy it. But all the dangerous things that happen, the radiation. I'm actually going to show you a supernova on the simulation here. Here's what a supernova might look like if the sun went supernova. When a supernova happens, you can see it blows all kinds of stuff outward. Gas, dust, matter. The star itself is basically being blown to bits, and that a lot of radiation, charged particles, nuclear particles, get sent out all throughout space. Gamma radiation, X-rays, really violent stuff that you typically only find in really intense environments like black holes. That radiation gets fired out in all directions. And so you can imagine a big sphere, a big ball that's getting bigger and bigger and bigger and has all that radiation. Well, the further out you go, the weaker that radiation gets. right? You're spreading out all this material over a larger and larger and larger volume. So if we're about 630 light years away from Betelgeuse, by the time that radiation reaches the Earth, 630 years after the explosion, it's going to be so weak that we're not really going to notice it. We're going to be totally fine. However, if we were within, I think the figure is about 300 light years. If there's life within 300 light years of a supernova, that's when you can start to get damage. And the kind of damage we're talking about is damage to our DNA that would cause basically high cancer rates, right? And of course, if you're much closer, the planet, the Earth, all of humans would just get vaporized by that radiation if we were really close to it. There you go.
Death to all humans.
Yeah, totally. So Betelgeuse would be a really fantastic thing to see.
There's a really great, just if anybody's interested in, or if anybody's worried about all the things in space that can kill them, there's a book called Death from the Skies by Phil Plait, and he goes through all of the things out in the universe that could possibly kill humans. And it's a really fun book.
That does sound really fun. I'm going to have to pick that one up. Phil Plait, I've read a couple of his books. He's known as the Bad Astronomer, and he's a really great science communicator, astronomer. He does a web series on YouTube called Crash Course Astronomy that's really, really interesting if you're looking to get into the basics. And I'll just type it. I'll try and post a link to it after the show. But there you go. Crash Course Astronomy.
Yeah, those videos are really, really great.
Yeah, they really are. They really are. So, so I think without further ado, we're past the top of the hour. Thanks a lot, Jesse. This was a lot of fun, man. It's always great to have you on, have you around, talking about your stuff, hanging out, talking about space, right? We've done podcasts together. We've done radio shows together. Now we're doing live streaming together. What's next? I don't know. Is there anything you want to talk about or
I don't know.
Or
the sky is the limit.
Is there anything you want to recommend or plug or talk about that you're working on or that you're doing? No is a perfectly acceptable answer.
But I got nothing big at the moment.
What's your social handles? What's your Twitter? What's your... For the 12 remaining viewers, you can go follow...
on Twitter, I'm just...
Go follow Jesse.
For all 12 viewers, you can find me on Twitter. That's like where I'm most active. Just at Jesse Rogerson. Yeah, find me there. I'm always posting random cool stuff about space and talking about space. So, yeah, go find me there.
Perfect. Thanks a lot, Jesse. And that's basically going to do it. I've got one more plug. A good friend of mine who's a really amazing musician. If you're looking for a stream to watch right now, from 8 till 9, and the rest of the week, he's streaming every night. His name's Bob Wagner. He's a great musician who's played for We Will Rock You, which was the Queen Broadway musical. So he's played live on that. He's in a number of bands. He was on the Kiss Cruise with his band Simply Queen, which is a Queen cover band. He's just a really fantastic musician, really great guy, and he's just doing streaming for the sake of it over the next 5 or 6 days. And so I'm going to post a link to his stream in the chat, and then that's basically going to be it. So let's copy that stream link for Bob. You should go watch him now because he's probably already underway and having a good time. But for those who did tune in, thanks a lot. For those who will watch this later, feel free to come and do the next live stream, which I don't know when it's going to be. Maybe this Friday, maybe later. But we'll talk about it. I hope the feed wasn't too bad, but we did our best and we're having lots of fun. And if you do have questions that you want to leave in the comments, we will try and answer those in future episodes. So until next time, clear skies, and I'll talk to you soon. Have a great one. Goodbye.